This example has two parts. For the first part, we're going to complete a table by finding 5 solutions to the equation y equals negative 2x plus 1. In the second part of this question, we will plot those solutions on the given graph and see what happens. To complete the table in the first part of this question, we will need to begin by picking either an x value or a y value for each of the 5 solutions we want to find. For example, I could begin by picking an x value of 2. So what I'm going to do off to the side is say, let x equal to 2, and I will substitute 2 in for the x in the equation. So y equals negative 2x plus 1 becomes y equals negative 2 times 2 plus 1. And we'll go through and figure out what is this y value. Well, negative 2 times 2 is negative 4. Negative 4 plus 1 is negative 3. So we have found when x is negative 2, the y value will be negative 3, and that will give us a solution, an ordered pair, of 2, negative 3. The choice of the 2 for the x value was completely arbitrary. We could have picked any other value for x, or we in turn could have picked a value for y. To change this up a little bit, I'm going to begin finding the second solution by picking a value for y. I'm going to pick, again somewhat arbitrarily, negative 1 for my y value. So we'll begin again by just formally stating let y equal negative 1. To remind myself what it is I'm doing, I will put negative 1 in for the y value, and so that will give me negative 1 equals negative 2x plus 1. To solve this equation, again, we follow our standard solving process. I will first isolate the variable term by subtracting 1 from both sides of the equation. This gives us negative 2 equals negative 2x. I will then solve the equation, negative 2 equals negative 2x, by dividing both sides of the equation by negative 2. And this tells me that a solution that has a y value of negative 1 must in turn have an x value of positive 1. So another solution for this equation is 1, negative 1. Now hopefully you recognize the amount of work we had to do to find that second solution was more involved than the work it took to find the first solution. Because the equation is already stated as y equals, the equation is already solved for y. So if I can pick x values, the work I need to do will be much simpler. So we'll go back again, we still need 3 more solutions, and I will begin again picking values for x. So we have 1 and 2. Seems natural, maybe we want to pick an x value of 3. So I'm going to begin by picking x equal to 3. Again, noting down here, this is where the work is that corresponds to x being 3. And y equals negative 2 times 3 plus 1. Negative 2 times 3 is negative 6. Negative 6 plus 1 is negative 5. So that tells me when x is equal to 3, the corresponding y value will be negative 5, and therefore 3, negative 5 is a solution for this equation. We still need 2 more solutions here. So we already have x values of 1, 2, and 3. Let's go into some negative numbers. I'll pick an x value of negative 1. So if x equals negative 1, our equation that we're solving becomes y equals negative 2 times negative 1 plus 1. Well, negative 2 times negative 1 is 2, and 2 plus 1 is 3. So we now have a solution, x value negative 1, y value 3, so the ordered pair is negative 1, 3. So we have 4 solutions, we need 1 more. For a final x value, I will pick negative 2 for the x. So if x equals negative 2, then the y value is going to equal negative 2 times negative 2 plus 1. So negative 2 times negative 2 is 4. 4 plus 1 equals 5. So next value of negative 2 has a y value of 5, and the solution is negative 2, 5. At this point, we have the 5 solutions that we needed for the table for part A, so part A is now complete. For part B, we now need to plot those 5 solutions on the graph. Before I can plot any points on a graph, I need to make sure the graph has some structure to it so everybody reading the graph will be able to interpret it in the same way. As a starting point, we need to make sure we draw in the x and the y-axis. We need to make sure we put arrows on at least the positive ends of the axes to indicate these go on forever in both directions. And we definitely need to make sure we label the x-axis with an x and the y-axis with a y. We also need to make sure that we put a scale on each axis. Looking at all the x and the y coordinates I have, they all fit between 1 and 5. So I understand if I set a scale of 1, 2, 3 on the x-axis, and a scale of 1, 2, 3 on the y-axis that'll be able to fit all of these 5 points in the graph. We want to remind ourselves 1, 2, 3 on the x-axis on the right side definitely indicates on the left side it would be -1, -2, -3. And same thing on the y-axis. The top goes 1, 2, 3, so the bottom part of the y-axis is -1, -2, -3. It is important to note that some instructors have different requirements in terms of how you scale your axes, so you will want to talk to your particular instructor to figure out what their specific requirements are. We'll now go through and plot the 5 points that we came up with. So starting with the first point, 2, -3. We begin by starting at the origin, and from the origin, we now need to move 2 units to the right to get to an x value of 2, and 3 units down to get to a y value of -3. So that gives us our first point right there. For the point 1, -1, we again go back to the origin. We will go to an x value of 1, which means right 1, and we go to a y value of -1, which means we need to move down 1. So our second point is here at 1, -1. To plot the third point, 3, -5, we again begin at the origin. We go to an x value of 3, we go to a y value of -5, and we plot our point at 3, -5. To plot the point, -1, 3, we again start back at the origin. We go to an x value of -1 and a y value of +3, so left 1 and up 3. And finally, to plot the point -2, 5, we again begin at the origin. We go to an x value of -2 and a y value of +5. In plotting these 5 points, something should definitely stand out in the graph. You should recognize that it appears these 5 points lie on the same line. One of the reasons we call these linear equations is when we do plot the solutions for any one of these equations, we will always obtain a line. If we take a ruler and line a ruler up with those 5 particular points, we should find that all 5 of them do line up on the edge of that ruler. And so what we can do is we can then draw in that line. And that line actually gives us all the solutions for this particular equation. When we remove the ruler, we see every possible solution for this equation. We call this the graph of the equation. By calling it the graph of the equation, what we're indicating is that every point on this line is a solution for this equation, and in turn, any other solution we would find for this equation would also be on this line. The truth is that while I had to stop drawing because I can't draw forever, there is no end to the number of solutions that this equation has. There is no end to this line. The line, just like the axes, does actually go on forever in both directions. And so we'll put arrows on both ends of the line to indicate this, that there is no end, that should I extend the graph out further to either side, I would find more solutions as well.